Okay, well, thank you very much. So I'm Olivier Dewitte. I'm physical geographer at the Royal Museum for Central Africa. And I'm going to present you some key results on landslide hazards that have been obtained over the last 8 years. So at the moment when I started my position here. But before I go into the details, I would like to stress that these results have been obtained with strong partnerships from different institutions and with about 10 partners in Africa. And I have listed here the name of the PhD student we have been working with over the last few years. So when you look at landslide susceptibility at the global scale, so this is the map that you have here in the southern part of the region, you realize that the western branch of the East African Rift is one of the landslide hotspots in Africa. So the lighter the color, the more susceptible the land is. And when you start to look at the population characteristics in those regions, for example, the map here above, which is the probability of urbanization, it's a scenario for the next decades, then the hotspot in Africa becomes one of the most exposed places to landsliding in the world. So we are clearly in an area where you have landslide problems. And more specifically, I'm going to present results in the region along Lake Kivu here, which is in the south of the Virunga volcanic province, and in the northern part of Lake Tanganyika. So here in red, you have the main faults that are active along the rift. So we have a steep topography, you have seismicity, obviously. What is interesting also is that the rift is at the origin of a landscape rejuvenation. So for example, here on the graph B, you see that we have highlighted the rift shoulders. And then basically between the shoulders, we have what we call a rejuvenated landscape. So we have steeper slopes that are younger with midpoints that are migrating. And outside the rift shoulders, we have what we call a relic landscape. We are also right at the equator, so we have high magnitude rainfall events. And we have also a climatic context that allow deep weathering. So we are also in a place where you have high population density. So you have about 10 million inhabitants living here. And for example, in Rwanda, you have more than 500 inhabitants per square kilometers. And these population densities are highly growing and sometimes very vulnerable, are also associated with important environmental changes. And for example, you have lots of uncontrolled deforestation, especially in DRC in the current days. So that's an overview of the type of landslide processes that we have in the region. So we have very diverse processes. We have very large and old landslides, rock slides like here. We have much more recent landslides, very shallow, that are really triggered by rainfall. You see that from the color, we have different types of rocks, of weathered material. You see also that landslides can happen here in urban environment, like here in Bukavu, where I will show some examples. You clearly have direct impacts of landslides, like here landslides impacting directly mining villagers from a mining activity. And you clearly see also that road infrastructure, for example, can be at the origin of some landsliding. So the region is pretty large. So when we started to work there were only a few case studies about landslide, like specific events in specific locations, like in the city of Bukavu. So basically what we want to know here in the region, we want to know what the type of landslide we have. We want to know where and when those landslides occur or will occur. And we want also to know what factors control these landslides. And of course, the human impact is important in this. So for working in the region, we don't have a specific method. We are rather holistic. So for the regional investigations, we rely a lot on remote sensing from satellite products, from optical and radar products. We go also in the field, we look at time series, we look at the historical records, we look with citizen scientists, for example, as well. And we have the strong partnership with African institutions, which also drives some of our research as we try to meet also the requirement of the African partners. So one of the first results that we have at the regional level is the landslide identification. So far we have identified about 20,000 landslides from Google Earth validated in the field. And here in this map, I have highlighted two types of landslides, shallow and deep-seated landslides, the shallow ones being yellow. And that differentiation is important if you want to understand the risk, for example, is that shallow landslides will be very sensitive to what happens at the surface of the soil. So for example, they will respond very quickly to rainfall conditions, so you can be triggered by a few hour intense rainfall. But shallow landslide, it also responds to the change in land cover and, for example, to the deforestation. So having said that, looking at all this landslide distribution, we have built a regional susceptibility map with other covariates, for example, improved the lithological map of the region. And such a susceptibility model performs much better than what I have presented in one of the first slides for the global landslide susceptibility model. So that was one of the first steps to highlight the hotspot of landsliding in the region. And also, another inventory we have compiled at the regional level is to try to identify the landslides where we have a known date. So, for example, which day, which month, which year. And with that, we were able to demonstrate that all the recent landslides that have been recorded with an accurate date, about 300 occurrences, none of them are linked to seismic activity. All these landslides are linked to rainfall triggering conditions. So as this is highlighted here. And when you look at the annual distribution of these landslides, what you see that you have a peak of landsliding which occur here at the end of the wet season. So that's a peak of landsliding, and the dark, the black curve here indicates the precipitation. So you see that in May you have a bit less precipitation than the peak that is occurring in March and April. And this has implication to understand the landslide hazard in the region. So we know that landslides depend on antecedent rainfall condition. And for that, we've developed a new threshold approach in the region that combines these antecedent rainfall conditions with landslide susceptibility. So keeping in mind the model that I just presented before. And here, this is one of the threshold map that we have for the region. That's very regional, but it shows nice opportunities for early warning system in the future. And we clearly show that we have less rainfall that is needed when you are, for example, close to the rift shoulder, because you have already a land which is much predisposed to landsliding. So looking specifically now at shallow landslides, we've tried to look at the way they distribute exactly within the rift. And those shallow landslides are all recent. So they have all been mapped with Google Earth. So Google Earth covers about 15 years. So those landslides have maximum age of 15 to 20 years. And we've looked at the distribution with regard, for example, to the presence of the rejuvenated landscape, which is highlighted here by the dotted line. So on the figure C, you clearly show that we clearly see that in the Congo Basin, you have what we call the rhodic landscape, and towards Lake Tanganyika, we have the rejuvenated landscape. And what we show is that overall, we have more landslide rates that are present in the rejuvenated landscape, and which is due to the steeper slopes. We also have landslides that are overall more frequent in the rejuvenated landscape, but they are of smaller size. And for that, we have two hypotheses. One is that we have less regolith, so we are overall steeper slopes that are more recent. But also in the rift, you have more seismicity. So those recent landslides, they have not been triggered by earthquakes, but the long-term impact of seismicity may be that it fractures the surface of the rocks, or it fractures the regolith, so that you have smaller pieces of material that can slide. So those shallow landslides are recent. One of the reasons is that the vegetation regrows very quickly. And this is an example here where you have some landslides that have been triggered by tree removals, and then it regrows quite quickly. So we have looked also at the impact of deforestation on the shallow landslides. So here you have forest. 1 year later, the forest has been cut, and then 2 years later, you have some landslides that have occurred. And we show that about after deforestation, we have a peak of landsliding that will last about 10 to 15 years. So it's year zero when the trees are cut, and you see that progressively the rate of landsliding will increase and come back to a normal level, so to say, after 15 years. So knowing that shallow landslides are influenced by the rejuvenated landscape, knowing that shallow landslides are influenced by forest cover, what we have done, we have reconstructed the forest cover over the last 60 years using historical photographs in the region. We have linked for every year of forest reconstructed, we have linked landslide susceptibility, and hence we could compute landslide hazard over time. Combined with exposure vulnerability indicators, we have analyzed the risk at the regional level. So this diagram shows an overview of the type of processes that are associated with this landslide risk. And we have nice conclusion that over the last 60 years, we show that the risk is higher in the DRC, while it has the similar environmental condition as what you can have in the neighbor countries of Burundi and Rwanda. And we show that this is mainly due to two processes. It is due to deforestation, but it's also due to location of people on steeper slopes. For example, you have the booming mining industry that has forced people to move on steeper and more hazardous slopes. Now I'll show you some. Okay. Now I'll show you some example of local investigation, and so therefore we go with much detailed inventories. Here we are just along the city of Bujumbura in Burundi. So this is 1 million inhabitant people. The city is located here. It is sprawling a lot, and we have mapped all these landslides. So we have more than 1,000 landslides that have been mapped in the region. Which is interesting is that if you look at the map here, you see this gray line that separates from one side the relic landscape and the other side the originated landscape. So clearly we see a strong control on this landscape origination and the presence of nick zones. So we have also demonstrated that many of these landslides are active and many of them are sometimes also associated with human activities. And here this is an eye example of what we call a compound event. So we have a heavy rainfall that has triggered about 200 landslides at once in a couple of hours. Those landslides here represented in red contributed to the sediment budget of the river, so triggering debris-rich flash flood. But in the same time, we have mining activities, and some mining activities have been placed where deeper landslides have also been triggered that created dams along the river. So you have a dam that is created, you have a lake that forms, then a few hours after the lake breaches and created an extra flash flood that had an impact here in the city about 6 kilometers away from the hill slopes in the places where you had no rainfall at that moment. And that specific event killed more than 100 people. Another example here is on a slow-moving landslide. So we have large landslides. We wanted to understand how this slow-moving landslide behave. And here the Ikoma landslide is probably one of the largest recent landslides in the region. We show that it was not triggered by seismic activity or specific humid periods. And so we invoke here that mostly triggering of the movement is associated with the deep weathering that we have in some places in the region, which has also implication for hazard scenarios. And then we have looked at the current cinematic of the landslides with almost more than 500 satellite images, and we show that those deformations respond very well now with the rain seasonality. So we have performed the same analysis for this large landslide here in Bukavu. It's more than 1.5 square kilometers. You have 80,000 inhabitants in it. It's here, the center of the city of Bukavu. You see also that the city is highly built on landsliding. You have here the red polygons. And this landslide is few thousand years old, but still moving. So we have this kind of deformation that are appearing here. And using, for example, INSAR, UAV, and other methods, we show that the current deformation has a similar pattern as what we have in the natural environment like the Ikoma landslide. But which is very interesting is that we have some parts of the landslides that have accelerated over the last 50 years. And we show that it's due to the convergence of drainage network and leaking of the pipes that we have in the urban context. So where we show here also that human activities have an impact on landsliding. So there were the few examples that I wanted to highlight. So clearly, in a few decades, we highlight the role of the rift on the landslide hazard. We highlight the role of rainfall, of course. Seismicity, we didn't see any earthquake-triggered landslides over the last 60 years, but clearly it has a long-term role also on the influence of the weathering condition, if I may say. And so that's work in progress. So we are progressively trying to fill in the research gaps in the different topics that are highlighted here. And with that, I thank you.
Excellent. Thank you very much. There's time for a few questions. Let's start with one that I was thinking of. These 20,000 landslides from Google Earth, did you analyze them by hand?
Mostly by hand, yes, at the beginning. So because we are in a context, we have two types of landslides. You have the recent landslide that can be easily identified. So we have developing new method now to detect them automatically. But once it comes to really know what is the source area of the landslide, is the landslide associated with forest cover change? Is the landslide associated with the road network? So there are some work in progress that I haven't presented here. So we validated everything visually. And then for the large landslides, its automatic methods are very difficult. So there's some work that have been carried out in other regions when LiDAR information is available. But here we don't have such product. And in addition, we have places where it is highly forested. So automatic detection would be very difficult for these landslides. But now we have work in progress to make things more automatic and extend the inventory over the entire Rift branch.
Yeah, exactly. That was what I was aiming at. But how does this automatic extraction actually work? What kind of data do you take? Is it only imagery, or is it also digital elevation models?
So that will be several steps. So first of all, with imagery, so like optical images and seeing like change detection of NDVI, for example, or vegetation indexes. Then this will be used and together with tools that have been developed by colleagues in Strasbourg, so which use machine learning and uses extra information, for example, morphometric information from the DDM. And then one constraint that we want to also better narrow is the time of the landslides, because when you look at optical images, it's frequent that you have several months without any image that are available. And if you want to come to better prediction and better, let's say, understanding of the role of rainfall of these recent landslides, we need much narrower time periods. So we will combine this also with SAR data.
Excellent.